Okay, welcome, and we were discussing about synchronous machines. Synchronous machines are huge capacity machines. It may be 100 megawatts. Okay, voltage is also higher, maybe 10 kV voltages of that level of power we are talking about, which in case of induction motor it is, because induction motor operation, 3-phase induction motor operation, large motors are there, but it also you cannot go beyond a certain capacity because of the fact that it draws magnetizing current from the supply. In case of synchronous machine, because there is a armature winding and a DC winding which is called field winding, this is armature, and field winding which is DC called excitation current. Excitation current is totally independent of the AC voltage that will exist here, quite independent. One thing I was telling, and before doing any mathematics, several things we now know about synchronous machine. One thing is this: I am going to excite this field winding with a DC, it will produce a stationary field. Stator, if it carries 3-phase current, 3-phase winding, it will produce a rotating field. These two cannot produce any torque if it is stationary, or if the speed of the rotor, physically you have to run the rotor to make this field Fr a rotating magnetic field, that is the thing. And therefore, it must be, rotor must be running at synchronous speed Ns, where the frequency on this side is a 3-phase supply. Then only this machine will work, either as a motor or as a generator. And another thing should be also interesting to note, that here this DC current is flowing, all the fields a stationary observer will conclude they are moving with a speed ns with respect to him in such a scenario. Now, this field, if you see, will there be any AC voltage induced in the field winding? Can there be any AC voltage induced in field winding? No. In steady operation, because there is no time varying field moving past it. However, there will be induced voltage in the stator coils, because with respect to stator, stationary observer, Fs, Fr are present. Therefore, there will be induced voltage in all of the stationary coils, but in the field coils there will be no AC voltage induced. Current in this coil will be simply that Vdc divided by whatever resistance of this coil is there. See, these are the things we can immediately conclude of a synchronous machine what it is. Then I was telling you that suppose I now know that a synchronous machine, stator winding, some 3-phase supply to be given, I want to run it as a motor. I know there is a rotor coil which is to be excited by DC, and if the rotor is stationary initially, if I energize this from the supply, I want to run it as a motor. So, supply is to be given. So, I will connect this supply and also I will excite the DC field. Is the machine going to rotate? No. Why? Because rotor field will remain stationary, because rotor itself is at stationary condition, but stator, the moment it carries 3-phase current, a rotating field is produced. Therefore, torque production will not be there. Therefore, how to run it as a motor? One very crude way I am telling, that way your thought process will improve. What I am telling, however, because I know when the torque will be produced, I can do one thing. This rotor, first I will connect it to a prime mover, and I will make its speed equal to the stator field NS. Then I will switch on the stator supply, then it will work, and then I will remove the prime mover. Are you getting? Not a very good way of starting synchronous motor, but physically it should work. Suppose it is a 4-pole machine, 50 hertz supply, 1500 RPM is the stator field I know. So, I have this one stator supply, I want to run it as a motor, whatever little I know about synchronous machine. What I will do? I will excite this with DC, but I am sure it is not going to work. So, I will first run this with the help of some external agency and bring its speed up to 1500 RPM, and then I will excite this field, and then I will close this switch. You will see it is running fine, torque is produced which will balance the load torque. This you just without any mathematics, these things can be easily understood. Anyway, so this was the thing we was discussing. So, this is the basic structure of the synchronous machine, and I was telling you about the voltage equation of the machine. This was the last slide. Generator mode of operation, it has developed this voltage. Now, this is the prime mover, you run the machine, this is stationary. So, rotating field will flux linkage will take place, there will be induced voltage, per phase induced voltage will be this. This phi will definitely depend upon IF, flux per pole, is not 4 by P B max LR, but it will depend upon this field current. Therefore, if field current is 0, suppose this pointer is here, field current will be 0, it is a potential divider connection, there will be no induced voltage. So, increase the field current by moving this jockey, your flux per pole will be created and induced voltage is directly proportional to this. Speed I am keeping constant. Okay. If you want to generate 50 hertz voltage, how speed get constant? I know what is the speed I have to drive this machine so as to generate 50 hertz. I will calculate it like this, N is equal to 2f by P. So, you can generate any frequency. Suppose I want to generate 40 hertz. If I know the number of poles for which this machine has been wound, I will be able to calculate it like that. Suppose I want to 4-pole machine, I want to generate 50 hertz. Then I can calculate what is this speed. It will be 1500 RPM. If it is a 2-pole machine, you have to run the prime mover at 3000 RPM to generate 50 hertz. So, the frequency consideration decides what should be your prime mover speed if you know the number of poles of the generator. That is what I am trying to tell. So, anyway, I have been able to generate AC voltage here, which will be balanced 3-phase voltage, but nonetheless it is not carrying any current. Okay? It will not carry any current. If you wish, you can have a 3-phase load. What for I have generated the power? To supply some load, 3-phase load, which may be inductive, capacitive, whatever it is, balanced load we will consider. So, if I close this switch now, there was some voltage, I would expect there will be balanced 3-phase current, and balanced 3-phase current means that rotating field will appear, and in case of generator mode, electromagnetic torque will be opposite to prime mover torque. So, prime mover torque has to increase, there will be some dynamics, and your load will be supplied with some load angle. This is the picture I am telling you. But you see, we in this class we will consider the operation of the synchronous motor, which will be connected to the bus. What is a bus? First let us try to understand. Your 3-phase supply system. Here bus and infinite bus. What is the meaning of that? It means that there is existing 3-phase supply already available. Who are the fellows who are making this alive? There are so many generators already connected in this system in parallel. And not only that, the eastern region have hundreds of generators, they are connected in parallel. Western region, southern region of India, there are hundreds of more than thousands power stations are there. All the generators you will find they are connected in parallel, and they are making this voltage alive. And when many generators are connected in parallel, these voltages, existing 3-phase voltage, whatever is available now in my lab, for example, in your lab, this can be considered to be a almost like a infinite bus. Now, the question is, what is the property of infinite bus? Property is this: the voltage of this line to line voltages I will not be able to change by sitting in my lab. That is decided by so many generators. I will draw a single line diagram to give you the idea. So many generators are there connected in a bus. Many. Achha, if you find out the Thevenin's equivalent of this bus voltage, what it will be? It will be, I know how to find out. Suppose all the equivalent impedance, all the impedances will be in parallel. So, equivalent impedance will approach to 0, is not? And then I know how to calculate the open circuit voltage. Suppose Thevenin's equivalent I am finding out. Therefore, the series impedance of this whole thing equivalent will be almost like a constant voltage, that is all. So, infinite bus is one where the voltages will be constant as well as frequency is constant. Voltage constant, frequency constant. Then such a available voltages is said to be a bus voltages. Loosely it is called bus voltage. That means voltage is constant. Terminal voltage available here. And what I am telling is that by doing something sitting in your lab, you will never be able to change these voltages and the frequency of this supply system. It is decided by so many generators already connected in this system. So, we will assume a bus like a 3-phase supply, suppose 440 volt supply in your lab. It is ultimately coming from the existing power system by stepping down the voltage etc. using transformer. But this voltage, suppose the phase sequence is A, B, C. In my lab, this is supply AS, BS, CS, supply 3-phase 440 volt is available. And this voltage and frequency is constant. and I will connect my synchronous machine to this bus and will make it operate either as a motor or as a generator. Not that a synchronous motor is locally supplying some load here. That you can do, but this is not the purpose of this course. Is that clear? So, first thing is what should I do? Suppose you have, I will draw it like this. Suppose I have my motor here. This, as I told you, I will not do any mathematics. First, let us try to understand the idea. And here is your field winding. Here is your field winding, and it has produced some field, rotor field. And I know the supply frequency, I know the number of poles of the machine. So, I know at what speed this rotor must be rotated, so that here 50 hertz voltage will be generated. This is stator coils. Okay. So, suppose I say this is A phase of the machine AM, B phase must be here, because rotating field is moving like this. Whatever is happening to this, that is why I call it B phase, and then this is C phase. This AM is machine. Suppose in your lab you have a small synchronous machine. So, AM, BM, CM. Now, I will run it at a speed which is equal to 2 F by P, so much RPS. By whom? By a prime mover. I will run it, and then I am sure there will be induced voltage in each of the coils, which will be balanced 3 phase. Fine. Now, suppose I say I would like to connect this with the bus. What do I do? You must be knowing, to connect two voltage sources, this becomes voltage sources. This to this, you just with your eyes closed, you cannot connect AM with AS, BM with BS and CM with CS, because you must make sure the instantaneous voltages existing at those points, they must match and the phase sequence must be same. Then only a successful connection will be there, otherwise there may be disaster. Is that clear? So, that is the thing. So, what I do, I will connect it in parallel. I will do like this. I will take 3 lamps. See, the topic is how to synchronize a synchronous machine with the bus, with the existing bus. These are the bus, this side is bus voltages, 3 phase. So, I am telling how do I connect this. So, it is first I will operate it as a generator by prime mover at a speed which I have taken help of this frequency 50 hertz, whatever it is, I will run it. I am sure AC voltages has been produced. Here also exists a balanced 3 phase AC voltage, but should I directly connect AM with S, machine A phase, machine B phase, machine C phase? No. One simple way to do this is I will take 3 lamps, incandescent lamp. LM, and this BM I will connect another lamp L2, connect it there. Another lamp I will take L3. So, first thing I identify the phase sequence correctly, that I will do. Some phase sequence meter is there and it is easy to identify the phase sequence. So, AM, CM, BM I will write, then between AM and AS I will not directly connect, I will connect a lamp. Similarly, between CM and CS I will connect a lamp L3, identical lamps I will connect. And then what I will do, across the lamps I will connect switches. This is a very interesting method. And these switches can be operated together, triple pole switch, that is indicated by this dotted line. They will be operated together. It is like this. Acha, now suppose, and let us take a concrete example, P equal to 4, number of poles of the machine is equal to 4. Then I am running it at 1500 RPM. Now, the question asked is, what will be the lamps, how they will glow? That is the question asked. Acha, first of all, you see, you have your, this point carefully note what I am telling. This is your bus voltage, supply side, AS, BS, CS. This is the, and all these phasors are moving with supply frequency F, that is 1500 RPM or 3000 RPM electrical, it is moving. I have connected a lamp between this and this point. I must know what is the voltage which is appearing across each lamp, then only I can say, okay, what is the voltage. And suppose this is the supply side neutral, which I have not connected, NS. This is the machine neutral, NM. Now, there will be similar phasors indicating the machine voltages, 3 phase balanced voltages are there. This I will use a different color. For example, I will use a green color, AM, BM and CM. These are 120 degree apart, you must understand. And this phasors too is rotating with same frequency F or NS, whatever you call it. Therefore, what will be the voltage between these 2 points, AS and AM? It is this length. It is across, this is the lamp L1 voltage, this is the lamp L2 voltage, this is the lamp L3 voltage, is not? Now, the question is, when this, suppose there was a switch here, I generated the AC voltage, AM, BM, CN was independently existing, moving with frequency omega, whatever it is, AS, BS, CS also existing separately with AS, BS, CS moving. Now, at some point of time, and this was open, this switch was open. Therefore, okay, that was there independently, they are existing. The moment you close this switch, because these voltages are balanced, it can be thought of Nm and this Ns with respect to this I am measuring the voltage, I can go by loop. But I do not know really when I have closed this switch where Am, Bm, Cm were compared to your As, Bs, Cs. It could be anywhere, I am not sure. This point must be understood. What I am telling, there is another switch here, which was kept open earlier. Am, Bm, Cm existed, As, Bs, Cs existed. Both of them are rotating with same speed, that is fine. But I am not sure about one thing, when I close this switch, where should I draw Am, Bm, Cm with respect to As, Bs, Cs? That information is not there. It could be anywhere. For example, it may so happen that your As is here, Bs is there, Cs is there, and when you have closed this switch, Am was passing through this point, just opposite. I am not sure. Am, then it was your Bm, and it was your Cm. You must try to understand this point. That is, it could be anywhere. I do not know. It may so happen they were overlapping, that is As, Bs, Cs, and it so happened that your machine Am was here, they were overlapping, Bm and Cm. I mean, hundreds of thousands possibilities are there, anywhere they could lie. So, I have drawn any arbitrary position, okay, it is like this. What do you think L1, L2 and L3 are going to do? They are incandescent lamp, mind you, our old filament lamp. Voltage across L1 will be this length, voltage across L2 will be this length, and voltage across L3 will be this length. So, all the lamps will glow with equal brightness. They will glow with equal brightness, and it will continue to glow. Question is, should I close? This is called synchronizing switch, and this switch, synchronizing switch. Should I close the switch now? Suppose it is in this position. Suppose it so happened that I have closed this switch and it was like this. In this case, what is going to happen? L1, L2, L3 will be equally bright and very bright, because the voltage As minus Am is twice this length across the lamp L1. Highest voltage will be in this position, and both of them are rotating at synchronous speed. Omega, this fellow is also rotating at synchronous speed. So, voltage across the lamp is the difference difference between the tip of this supply side phasor and the machine side phasor.
So, neutral will be connected now.
Neutral may not be connected, may be connected. with the other things it will come back, other supply side. There is a coil there. Anyway, but what I am trying to tell you is that if you imagine, okay, Nm and Ns are connected, neutral, to simplify matters. Nf and Ns are, that I can do, what is there, neutral connected. So, they are connected. So, it is like this. Now, the most interesting thing is, if the bus frequency and the rotor speed are exactly, and what will be the lamp voltage across the lamps? If it so happens that when you have closed the switch they are overlapping, it will be 0 0 0, all the lamps will be dark. Therefore, what should I do for synchronization? Which of these three instant is favorable? Obviously, when the lamps are dark, then I am sure instantaneous potential of ASM are same, BSBM are same, CSCM are same, and there will be no risk involved. You can close this switch and lamps will be bypassed, and it will be truly paralleled the machine terminals with the supply terminals. Is not? That is the thing we are looking for. But as I told you, you please think over, we will continue, but I want to tell you one interesting point. But if this speed of the rotor and supply frequency are same, exactly same, if you close this switch, it is very unlikely that this situation will prevail. It is a matter of chance, and matter of chance, that probability is remote. Every likely you will get a situation like this, because every instant is there. Therefore, I know the correct instant of synchronizing the machine terminals with the bus terminals is that instant when all the lamps will be dark, that is known. But making the speed of this rotor exactly same as the supply speed, remote chance of getting that correct instant appearing. Anyway, we will continue next time with this. Interesting. Thank you.